Welcome to Foundation Mathematics, Essential Background 2, Equations. The objectives for this session are to recognize symbols and their meanings, turn statements into equations where possible, be familiar with numbers, letters, and symbols, be familiar with terms, shorthand, and conventions in algebra, recognize common letters with special meanings, recap the BODMAS rules, change the subject of an equation, and solve an equation numerically or in terms of another unknown. Let's begin with symbols and their meanings. This symbol means doesn't equal. So for example, 3 does not equal 5. This symbol means approximately equal to. So 7.9 recurring is approximately equal to 8. This symbol means less than or equal to. So hours worked in a day is less than or equal to 24. This symbol means less than. So the number of days worked in a week is less than 8. This symbol means greater than or equal to. So the number of hours studied is greater than or equal to 0. This symbol means greater than. So wages are greater than 0. Any expression which uses one of these symbols is not really an equation. An expression using any of the highlighted symbols is not an equation, it is an inequality. The language of algebra can be illustrated by using this example shown on your screen. The letters represent numbers. Remember that the letters could be fixed or variable, but usually, as we mentioned earlier, X, Y, and Z will represent variables. Notice that there are no multiplication or division signs in this equation. This is because multiplication is represented by putting the number next to the letter or letters. So 3 times x equals 3x. Furthermore, numbers are placed before the letters. This means that if we have y times 5, we would write this as 5y. And letters are positioned in alphabetical order. So if we had 25 times z times x times y, we would write this as 25xyz. An algebraic term is a small group of numbers and letters with no symbols, as shown here. An algebraic expression does not have an equals sign, as shown here and here. And an algebraic equation does have an equals sign, as shown here. Now let's take a look at a few examples of which statements can and can't be turned into an equation. Here's statement 1. The number of girls G in a class is twice the number of boys B. Therefore, we have that G equals 2B. Since there is an equals sign in this expression, this is an equation. Now for the next statement. The number of students in the first year F is greater than the number of students in the third year T. So we have that F is greater than T. There is no equals sign here, and therefore this is not an equation. And now for the final statement. The internet connection has been lost at least as many times this week, WT, as last week, WL. This can be written as WL is greater than or equal to WT. Again, there's no equals sign here, therefore, this is not an equation. We now take a look at another very important symbol, the implication sign, as denoted on your screen here. We know that sometimes equations can be simplified or solved. In order to go from one step to the next, we use an implication sign to denote the fact that one line follows logically from the previous one. So, for example, if we have 5x squared equals 125, labelled as equation 1, and we divide this equation by 5, we obtain equation 2. And of course we have the implication sign on the next line. And we have that x squared equals 125 divided by 5. This now implies that x squared equals 25, since of course 125 divided by 5 is 25. Square rooting both sides of this equation gives us equation 4, which is x equals root of 25. And finally, this implies that x equals plus or minus 5. Which letters should we use to represent numbers? In a real situation where the letters represent the value of something known, choose letters reminding us of that thing. So, for example, let C equal the number of cats my neighbour has. So, in this example, we have 3 cats, and therefore C equals 3. Let's now take a look at a more involved example. Suppose that the only pets my neighbour owns are cats or dogs. Let C equal the number of cats my neighbour has, and let D equal the number of dogs my neighbour has. Then the total number of pets, P, my neighbour has, is given by P equals C plus D, so the number of cats plus the number of dogs. If C equals 3 and D equals 4, then P equals 3 plus 4. So P equals 7. Letters from the end of the alphabet, such as X, Y, and Z, are used to represent some number that can have a range of values. Such a number is called a variable. So, for example, let X equal the income of an employee in a company. This is a variable because it varies from employee to employee. We now take a look at some common letters with special meanings. The symbol C can represent the speed of light. The symbol E is the natural number used in growth series and logarithms and is approximately 2.71828 and so on. The symbol I is root minus 1 and is called the imaginary number. The symbol J is often used by engineers instead of I to represent current and is also root minus 1. The symbol K can be used as an unknown constant value, and sometimes we use C for this as well. And T usually denotes the variable for time. Let's take a look at some examples of selecting letters for variables. Which letter do I use to represent a variable? The number of fans can be represented as V. The number of sofas as S. And the number of students studying biology as B. Before moving on, let's remind ourselves of the BODMAS rules. BODMAS is a useful acronym which informs us which mathematical operation should be performed first. First, we carry out the operations inside the brackets. Then we carry out the orders or powers. Then division. Then multiplication. Then addition. And finally subtraction. Let's now take a look at an example of how we can create equations from statements. Suppose that all my wages this week have been spent on packets of rice and tins of soup. We are required to express this as an equation. So let's solve this. We can write this in an equation form as wages equals cost of a packet of rice times the number of packets of rice I've bought plus the cost of a tin of soup times the number of tins of soup I've bought. We can express this more concisely by replacing the words with symbols or letters. So if we let W equal weekly wages and we let A equal the cost of a packet of rice and R equal the number of packets of rice I've bought and B equal the cost of a tin of soup, and finally S equal the number of tins of soup. Then we have this equation. W equals A times R plus B times S. Let's now see how we can find an unknown using example 1. So if we had the same example, all my wages this week have been spent on packets of rice and tins of soup. Using the equation found in example 1, find my wages for this week if I bought 15 packets of rice for £2 each and 18 tins of soup for £0.50. So let's solve this. From example 1, we have this equation, W equals AR plus BS, where the letters are represented as shown. So we have, if we plug in all these values, W, my wages, equals £2, which is the cost of a packet of rice, times 15, which is the number of packets of rice I bought, plus £0.50, which is the cost of a tin of soup, times 18, which is the number of tins of soup I bought. And tidying this up gives us £30 plus £9, which is equal to £39. Let's see how we can now change the subject of an equation. Let's take a look at an example. We have that W equals AR plus BS. Here, W is the subject of the equation. We are required to change this equation so you can solve it for A or S. So let's rearrange this first to solve for A. In order to solve for A, we need to isolate the term with A in it. We have W equals AR plus BS. If we subtract BS from both sides, we obtain W minus BS equals AR. Now we can divide both sides by R to give W minus BS divided by R equals A. And of course this should be written as A equals W minus BS divided by R. Now let's solve for S. in order to solve for s, we need to isolate the term with s in it. So we have w equals ar plus bs, and we need to subtract ar from both sides to give w minus ar equals bs. Now we divide both sides by b to give w minus ar divided by b equals s. And again, we need to write this as s equals w minus ar divided by b. Now let's see how we can apply these equations. Suppose we have this equation again, w equals ar plus bs. We are required to find the number of tins of soup I can buy if my wages for this week are £20. Suppose also that a tin of soup costs £0.50 and that I have bought 8 packets of rice for £2 each. So let's solve this. To find S, the number of tins of soup, we're going to use the formula in the rearranged form. S equals W minus AR all over B. So, plugging in all the values I have, we obtain S equals £20, which is my wages for this week, minus £2, which is the cost of a packet of rice, times 8, which is the number of packets of rice I bought, divided by £0.50, which is the cost of a tin of soup. Tidying up gives us £4 divided by £0.50, which is equal to 8. Now let's take a look at a few general rules to solve equations. Firstly, we need to get rid of any fractions involving the unknown. Then multiply out the brackets, and then put all the terms involving the required unknown on one side of the equation. And finally, factorize and divide by any remaining coefficient to solve. Let's take a look at an example. If we're required to solve this equation for x, then we begin by multiplying out by 10, since we're trying to get rid first of any fractions involving the unknown. This tidies up to this expression, 50 plus 4x equals 100 minus x. And notice that all the fractions have now disappeared. Next, we multiply out any brackets, but as there are no brackets, we don't need to worry about this step. Then we put all the terms involving the required unknown on one side of the equation. Clearly, there are x's on both sides. So, if we add x to both sides, we're going to get rid of the x's on the right-hand side. And so we obtain 50 plus 4x plus x equals 100. In order to isolate the x's, we now subtract 50 from both sides to give us 5x equals 50. And finally, we factorize and divide by any remaining coefficient to solve. So we need to divide by 5 to give us x equals 10. Now let's see how we can solve an equation in terms of another unknown. Let's take a look at an example. We're required to solve this equation for x. First, let's get rid of any fractions involving the unknown. Since this doesn't apply to this example, we need to worry about this step. Next, multiply out the brackets. So, this does apply to this example, and we have 6 plus 7y equals 5x plus 10. We've multiplied out 5 times x plus 2. Next, we put all the terms involving the required unknown on one side of the equation. so we need to subtract 10 from both sides to give us 6 plus 7y minus 10 equals 5x. Next we tidy up to give minus 4 plus 7y equals 5x. And finally we factorize and divide by any remaining coefficient to solve. So of course we need to divide by 5 since we need to isolate the x on the right hand side. And we have x equals minus 4 plus 7y divided by 5, which can of course be written as 7y minus 4 divided by 5. This brings us to the end of this session. If you have understood its contents, you should be able to recognize symbols and their meanings, turn statements into equations where possible, be familiar with numbers, letters and symbols, and terms, shorthand and conventions in algebra, recognize common letters with special meanings, recap the BODMAS rules, change the subject of an equation, and solve an equation numerically or in terms of another unknown. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.